Earth is pretty heavy. How heavy and how do we know that? How do you get Earth's mass? Hi, I'm a physicist, and to answer this we will find out what mass actually is. Dip into Newton's theory of gravity and use this odd-looking experiment to see gravity's strength. Our Earth is pretty heavy. As heavy as 81 moons or 4.3 million times all the water of all the oceans. The mass of the Earth is 5 septillion 970 sextillion kilograms. That's a 597 and 22 zeros. If we combine the mass of all humans living on Earth, we get 496 billion kilograms. So Earth is 12 trillion times heavier than all humans combined. Okay, our Earth is pretty heavy. We know this because, well, how do we know this? We know this because we measured it. Okay, but how do you actually measure Earth's mass? Overall, a lot of measurements were involved. Measuring times, measuring distances, and whatever this thing measures. But no mass. Actually, we're not even able to measure mass directly. We have to calculate it. Yes, scales seem to show mass, but as we've seen in this video, a scale does not measure mass. The mass of something solely depends on the thing's size and density, on how much is there and what it's made of. Mass does not depend on anything else. In particular, it doesn't change with your location. Scales measure something that indeed changes with your location. They measure weight, or connection to the ground. Scales measure how strongly gravity pulls on us. The strength of this gravitational pull depends on your mass. The greater your mass, the stronger the pull. That's why you can calculate your mass out of your weight. A scale is designed to do exactly this. It measures gravity's pull and then tries to calculate your mass out of it. But it's not just the weight you need for this calculation, you also need something called gravitational acceleration. This gravitational acceleration is a number telling us how fast things speed up while falling to the ground. Knowing this number and measuring gravity's pull, the scale calculates your mass. But for this to work, you must be standing on the Earth's surface. But if we take Earth's surface as a reference to measure the mass of something, how can we possibly figure out Earth's mass? To answer this question, let's go back to the guy who gave the unit of gravity its name. The apples fall down guy, Isaac Newton, whose theory we explain in this video and why the theory doesn't truly work but sort of does anyway. He figured out that the gravitational acceleration not only depends on Earth's mass, but also on its radius and some number that determines the strength of gravity compared to other forces. Newton called this number the gravitational constant, or big G. Big G for strength and small g for acceleration. For more insights into the incredibly creative minds of physicists, please subscribe and like if you'd like to. Unfortunately, Newton could not measure the number G, or Earth's radius, or Earth's mass. But he knew that if he had two of these numbers, he could figure out the third one, because they make up G. And he knew the value of the gravitational acceleration, so he could turn this around to calculate the missing number. Alright, first, Earth radius, the distance from Earth's surface to its center. Luckily, people had been measuring Earth's size since ancient Greece. A guy named Aristoteles figured it out around 200 BCE using rays of sunlight, their shadows, and some clever geometry. If you want to learn more about this, please leave me a comment down below. Furthermore, Indian and Arab astronomers in the Middle Ages made measurements and calculations that were later picked up and further developed by European science. Long story short, Earth radius is about 6,371 kilometers. Great, that's the radius. But the real challenge was figuring out G, the gravitational constant. Without G, you can't calculate the mass of the Earth. Newton was stuck with his theoretical framework, but he found no way to pin down real numbers. But an English scientist in the late 1700s did find a way, Henry Cavendish. Cavendish set up an experiment, an odd-looking experiment, which uses the fact that not just Earth causes gravitational pull, but every mass causes an attraction to other masses, always scaled by G. The attraction of not super heavy masses is normally just too small to notice for us, yet it can be made visible through this odd-looking experiment. Two balls with small masses attached to a stick, a hanging stick. Two bigger balls with bigger masses pull on them, or rather, they exert a gravitational force that pulls on them, creating a turning motion, made visible by a light ray bouncing off a mirror. By carefully measuring the twist angle of his turning motion and knowing the masses and distances involved, Cavendish could calculate g. His value wasn't perfect, but it was incredibly close to what we use today. Cavendish measured g to within about 1% accuracy. That is astonishing, because g determines the gravitational force between anything, anywhere. Knowing its value, we can ponder what holds both us and the entire universe together. Great, now we've got all the ingredients. The gravitational acceleration, Earth radius, and the gravitational constant. Plugging that into the equation, doing some math, and we calculated Earth mass. But there are some drawbacks to the Cavendish experiment. The biggest problem: gravity is the smallest force. Super small. The gravitational pull from small balls is tiny. As a result, the angle in the experiment ended up being very small. Since humans are not perfect, Cavendish might have made some mistakes while trying to read the angle. As if it wasn't hard enough already, things like small vibrations in the laboratory, changes in the ambient temperature, or even minimal air currents could distort the measurement. In order to counter this, Cavendish repeated the measurement several times. Thereby, he also used different masses, knowing that his balls were probably not perfectly round. But no matter how hard he tried, he could not counter the fact that his experiment was also influenced by the local gravity of Earth and nearby masses. To overcome all this, we have to go bigger. We have to switch from gravity due to balls to gravity directly from Earth. With the introduction of satellites in the 50s, that became possible. Earth gravity pulls on satellites. This pull determines the satellite's orbit. By analyzing satellites' orbits, we can determine Earth gravitational pull with high precision. The pull depends on the Earth and the satellite's mass, as well as on their distance. Knowing the satellite's mass and height, we can calculate Earth mass again. Thanks to tracking satellites' orbits, we can confidently state Earth mass. So, no matter if you want to measure your mass or Earth's mass, all you have to do is measure gravity's pull, use Newton's theory, and calculate the value. And that's how determining Earth mass actually works. If you want to learn more about Newton's theory, watch this. Thanks for watching. Please drop your questions in the comments and subscribe to find out how it actually works.